Can a computer tell us the answer to life, the universe and everything? And is the answer really 42? We're going to take a break over the next couple of videos from building our CPU, and we're going to look at algorithms and computers. So we're going to ask and answer the question, can we create a master algorithm that will solve all problems? And can we get a computer to run that algorithm to find a solution? So it's kind of like the famous book, The Hitchhiker's Guide to the Galaxy, in which they get a computer to answer the question of life, the universe and everything, and it comes up with an answer of 42. So first of all, we're going to have a look at what we mean by an algorithm, and we'll go through an example of an algorithm. So here's a simple algorithm here. The question is, what is the highest common factor between these two numbers, 3654 and 1365? Now what we mean is, what is the largest number that will divide into both of those? So in order to find that, you take the biggest number and you divide it by the smallest number. In this instance here, it'll give a value of 2, and the remainder would be 924. You then take the smallest number of the two above and divide it by that remainder 924, and that will again one time, and that will have a remainder of 441. And you continue that process. You take the 924 divided by 441, you get the 2, remainder 42, and you keep working down until you get a value of remainder 0. And the answer is going to be the value 21. So 21 is the highest common factor of these two numbers. So you can see here that the algorithm, if we were to write it out in words, we could say we divide the biggest number by the smallest number and find the remainder. We then we divide the smallest of the last numbers. Okay, so that's the smallest of the two numbers here, which is 924. And we divide it by the remainder, and we repeat that process all the way down till we get a value of 0, and the final answer is going to be this number here. Okay, so if we were to draw it out in a little diagram, it would look like this. So here's the flowchart. If you have the two numbers and you're looking for the highest common factor between these two numbers, you take the largest number. So let's assume the largest is A. So you're going to have A divided by B, and you get a remainder C. We then ask, is the answer 0? If the answer is 0, then the highest common factor is a value of B. So you can see that from above when you look at this one here. You can see here that we have a remainder. The remainder is 0. If the remainder is 0, the highest common factor is going to be that 21, which is our value B. So we say that this column here is column A, and that column is B. So if you get down to this point and the answer is no, then we come round and A becomes B and B becomes C, and then we work our way round this algorithm again. So you can see that again from above. We can see here that in this instance here, this is our A and that's our B, so you can see that the A there becomes the B, and the B here is the value of the remainder C. So we work our way round until we get a value of 0, and when we get that, we know that the answer is the value that's left, B. David Hilbert, a famous mathematician, he came along and formalised the problem, and he called it his Entschuldigung problem. So apologies for my German. It means decision problem. So we're still really asking ostensibly the same question. Is there some general algorithm for solving all mathematical problems of a certain type? Now this is a very loose interpretation of this problem, but it gives us something to start with. So we're still really asking, is there some master algorithm? Another mathematician called Alan Turing was thinking about this problem, and he came up with a thought experiment. He imagined a machine, which for the moment we'll call a Turing machine. And this Turing machine had at its input and output an infinite length of ticker tape. Now a ticker tape's just simply a tape with holes in it. So rather than thinking about it in terms of holes, we can think about it in terms of zeros and ones. Now this machine acted on these zeros and ones which were the input, and it threw out, in the end when it had finished working through its algorithm, it threw out an output. So take for example, here's our input, and when it's worked through this particular algorithm, it gives this particular output. So this really is just another way of thinking about our algorithm. It takes an input, it works through a process and gives us an output. So here's an example of an algorithm which is going to be ran via the Turing machine. If we think about the Turing machine as having a particular state, now I'll explain that just in a minute, but the state of the machine could be any number, 0, 1, up to a million, billion, whatever. It then receives an input, so the input is the value that's on the ticker tape, so that's just our zeros and ones coming into the machine. So depending on its internal state and the input that comes in, it can either retain that state at the same value or it can change it. It can then change the value of that input to another value or retain that same value, and then it will move the ticker tape one position to the left or the right. So that's all that machine will do. So what about this internal state? Well, what do we mean by that? Well, whenever we build up our CPU, what's inside here will be different registers and accumulators and memory locations. And our internal state, if you like, is a snapshot of the values in those components at that point in time. So it just tells you what position the machine is sitting in at that point in time. And if you like, we can create a number for that position. And this internal state is just that number. So if we talk through some of these, we could say where internal state 0, the input's a 0, then the internal state remains a 0, the input remains a 0, we move one position to the right. If the internal state is a 0 and we receive a 1, then we get into a different internal state, let's say some random internal state, we call it 13. And the input then remains at 1 and we move one position to the left. If we're in internal state 1 and the input is a 0, we go to internal state 65 and we change the input to a 1. And then we move one position to the right. If the internal state is a 1 and the input is a 1, then we leave that internal state as a 1 and we change the input to a 0 and we move to the right. If we're in internal state 2, and the input is a 0, then we go to internal state 0 and we change that input to a 1 and we move one position to the right and then we stop. So this is an example of us running through an algorithm in our Turing machine. Now the problems that we're going to have here is that we're going to have instructions. So instructions are going to tell the Turing machine how to act, but we're also going to have data on the same ticker tape, and we have to be able to distinguish between the data that's on the ticker tape that we're acting on and the instructions which tells us the Turing machine how to act. So we're going to have some sort of code in order to allow the machine to tell the difference between the instruction and the data, which all sits on the ticker tape. So it's all the zeros and ones all together. So let's go ahead and we'll see how to do that. So let's see how we can write our instruction and our data in one stream of ones and zeros in a manner that our Turing machine can come along and it can read it and it can know which parts are instruction, which parts are data. So I've got the top line here and you see it's just a bunch of zeros and ones. There's actually 19 of them running all the way along. And I've got another line down here, the third one down, and that's just another bunch of zeros and ones. There's 19 of them running along that line there as well. Now we're going to form a code here. Now the code is going to be quite simple. It's going to say When you get a 0 and a 0, that's represented by a 0. A 0, 1, 0 will be a 1. 0, 1, 1, 0 will be a 2. 0, 1, 1, 1, 0 will be a 3. And 0, 1, 1, 1, 1, 0 will be a 4. So on and so forth. So you can see how that's going to continue. So we apply this here to what we have above. Then we can look and see the first three here. You see you've got 0, 1, 0. That's going to give you a 1. And then you take this one here. The 0 and 0 will give you a 0. The 0 and the 0 will give you a 0. And then again you've got the 0, 1, 0 will give you a 1. And you've got the 0, 1, 1, 1. 0, 1, 1, 0 will give you a 2. You get the 0, 1, 0 give you a 1. 0, 1, 0 give you a 1. And again this one here is going to be 0, 1, 1, 0 give you a 2. And then a 1. And you have to be careful when you get to the end here, because you're going to have the 0, 0 from this line here, which will give you a 0. And then the 0, 0 here will give you another 0. And then you have the 0, the triple 1s will give you a 3, so on and so forth. So you can see how that's going to work out all the way along. So what we can do is we can take the row 2 and row 4 and we'll put them together in one line. So row 2 and row 4, well, what have you got? You've got 1, 0, 0, 1. You've got a 2. You've got a 1, 1, a 2, 1, 0, 0, 3, 1, 1, a 4, a 0 and a 2. So you can see here that we're actually going from our binary format here to actually a decimal format. So you can see here that this value here, which is in our binary 0, 1, 0, is represented by a number 1, a number 2, number 3 and number 4. So now it's all up to us and how we decide we want to define these things. So if I wanted to, I could say that the 2 is a comma. Okay, so every time you say a 2 is a comma. And you can also say that this binary format here, we can put it in decimal. So that's the decimal for 9. So it's 1248, which is a 9. So you could say that line then becomes 9, comma, and that would be a value of 3. And then there would be another comma, and that would be a value of 4. And now we're at the other point here. Now we chose 2 to be a comma, but the value 3 could be anything, okay? So we're just deciding the value 3 is some instruction, and we'll just call it instruction 3. And then again you've got the number 3 there as well, which is just the binaries. So the decimal for that is just the value 3. And again you've got another value 4. And we can choose what we want to use that for. So we can choose that for an instruction, and we just call that instruction 4. And then you've got a value of 0, and then you've got your 2, which is your comma. So we could say that these two lines here, which are, it's 38 zeros and ones, can be actually represented in this format here. So 9, 3, 4, instruction set 3, 3, instruction set 4, 0, comma. So this here, in effect, it contains our data and our instructions. So our data is going to be our 9, and our 3, and our 4, and our 3, and our 0, and our instructions here is going to be instruction 3, instruction 4. And of course we could continue on with this, we could have instruction 5, 6, 7, 8, 9. So this is a neat way which we can call contraction, in order to represent the data and the instructions all together in one line in a format that the Turing machine is able to decipher. So let's take this little code that we've developed and we've called contraction, and we'll see in the next video whether a computer can answer the question of life, the universe and everything.